Hi, my name is Curtis Anderson. I'm a senior software architect at Panasas, and I'm going to walk you through the internal design of the product that we just announced, the ActiveStor Ultra. Thank you. And the technology that goes into it. There we go. So, I have to give you a little bit of background on what PanFS is. It's a parallel file system optimized for HPC. We separate metadata processing from data processing. The metadata processing happens on what we call a director, and the data storage is on a storage node. You'll see me change the name of that storage node later in the presentation just to confuse everyone. Our architecture has a third component, which is a client-side plugin that uses a proprietary protocol to talk to the other two pieces. That's called the direct flow client and the direct flow protocol. That's what allows us to do the parallel file system piece of it, the parallel delivery that gives us the performance. Oh, back one. There we go. So, what is PanFS? PanFS is a POSIX file system layered over a scale-out object store. So all the benefits you would expect out of an object store in terms of scale-out, linear scaling, resilience against failures, all those, we have that, but we have a traditional POSIX file system on top. Yes?
Think about just to put the microphone just next to your chin, almost like that, then we can really hear.
Oh, sorry. Yes, I'm getting etiquette on my microphone usage. So, I have to point out that since the beginning of the company, we were founded in 1999 as one of the very first generation of parallel file systems. I'm not quite sure if we were the first, I think so. We have had this same architecture, so POSIX over an object store. I mentioned that we're separated metadata onto director nodes and data on the org. Oh, that's what's happened. Yes, I was off by a slide. OSDs are the object storage devices. That's the main storage target in PanFS. Metadata is processed by the director nodes, but it is actually stored on the storage nodes along with the user file data content. We use erasure coding per file, and each file is spread across all of the object storage devices in the system. That's how we get the resilience against single node failures and multi-node failures is with that network distributed erasure coding. If there is a failure, we reconstruct the pieces that were missing of the various files using all of the object storage devices in the storage, the object pool. That gives us an increasing amount of recovery performance as the scale of the storage pool increases in size. That increase in performance turns into a decrease in elapsed time when you're after a failure, when there is a potential exposure for loss of data. And so that's the reason that we say that the risk of the data reliability of the system increases as the scale increases. Yeah, data reliability increases as the scale increases rather than decreases. In a traditional architecture, data reliability decreases as the scale goes up because of the way the rebuild times don't scale up with the total capacity. Okay. So now I'm going to go into the internals of what's inside a Panasas OSD. As I said before, the OSDs implement the direct flow protocol. The direct flow protocol is actually a combination of iSCSI and RPC interfaces. So what that means in particular is our objects are defined by SCSI T10 rather than by the S3 protocol. So they're not the same objects you would find in most other scale-out object stores. On the other hand, there really are objects that the object storage devices maintain a set of metadata that's private to the object storage device that's not visible outside. Things like the actual location on the storage devices, on-disk formats, free space management, etc. We do support snapshots, and so that's also handled here. The metadata processing asks all the object storage devices to create a snapshot, and they all do that in parallel. So it is an object pool in that sense, but it's defined by T10. The T10 object that you might not be familiar with is a set of SCSI commands that's part of the formal spec. We contributed that to them at the time, like 2003, 2004, that we were implementing this. Let's see, so the next level of detail. So this is how the architecture treats an object storage device in Panasas. So what is Ultra? ActiveStor Ultra is the next generation of our object storage devices. It is a brand new software stack running on commodity hardware. We call it portable rather than software defined because we want the ability to customize the software for the particular piece of hardware so that we maintain our appliance manageability for that piece of hardware. Software defined, you just put the software on a piece of hardware and you hope that it has all the right characteristics. It's the customer's problem if it doesn't. We want a little bit more control, so we do that integration ahead of time. But it is a high performance cost platform, and so you get the cost benefits and the volume benefits that come with COTS. We actually use NVDIMMs for power fail resistance. We have the latest networking technology, in this case 25 gigabit Ethernet and InfiniBand. With this new base, software base, we can actually generate more and different shapes and types of object storage devices, not just a one-size-fits-all, but variations on a theme. And I'll tell you next about the software, but in general, it's user mode software layered on top of a bunch of open source packages layered on top of Linux. So it's all the things you would expect out of Linux, except that we're managing the distribution for you rather than you having to reach in and do your own security patches and whatnot. Okay, so now you're seeing in the diagram the full structure of the architecture. I'm going to go to a bunch more detail in here about why it is that PanFS does so well at mixed workloads and at combinations of workloads at the same time. So most storage systems that have flash and hard drives the way we do, the hybrid storage devices, they tend to use the flash as an LRU cache of storage, or maybe something a bit more intelligent. We actually have a static division of labor between the different storage devices. So the key observation is that hard drives are very good at delivering bandwidth if you give them something very large to work on, large sequential transfers, if you don't interrupt them with small transfers. So we selectively place large files on hard drives. We also include in the object storage device, the system, SATA SSDs. They're cost effective, they have zero seek time, and we put small files there. Now, metadata, in our older generation of products, we also put metadata on those SSDs. But it turns out, after us looking fairly deeply at it, that metadata is a much more latency sensitive workload than small files are. So, and they are not particularly variable in size, metadata objects. So we put those into a database, and we put that database onto an NVMe stick. So we're getting the combination benefit of the raw performance of the NVMe drive for metadata operations and the different indexing and caching mechanisms that come with a database for the metadata. The nodes, we also have DRAM for caching, of course. I'll tell you this specifically in a second. And we have NVDIMM for our transaction log. So the combination of those, every device being used for what it was intended for, is one of the reasons we have such good, as I said, mixed workload performance. Where to go next? So the NVDIMM intent log, it has an interesting side effect on the software. We want to provide a stability guarantee to the client and to the application, but we don't want to wait for a piece of data to go all the way down to the underlying storage device. So we log it into the NVDIMM. What that means is that the open source packages between our software and the actual devices, they can run in traditional Linux full async mode, because our transaction log at the top will replay the operation from the beginning and make it right if there's a failure in the middle. Linux file systems and storage technology in general is optimized for that case of running in full async mode. When you put them into synchronous mode, then ODirect or one of those, then they're less efficient and just their overall performance is less. So we think of that as an advantage. Let me keep going here. So one of the things that we have built into the software architecture for version 4 of the OSD software stack is what we're calling a 3-tier data placement. So like I said, the earlier large files onto the SATA hard drive, small files in the SATA SSD, and metadata in the SSD. That brings us to what we traditionally called a balanced architecture. We're selecting open source hardware that is balanced in the sense that the recipe for building an OSD is we start with the storage drives themselves, hard drives, flash drives, and sum up their performance, and then we make sure we have network interfaces that will support that much performance. We have just enough CPU in between to drive each end of it. The goal we're looking for there is to keep all of the drives busy all the time, but without having any excess CPU or network bandwidth or something else sitting around. We want to keep everything balanced. If something were over-provisioned, that would just be extra cost, a waste. And so that's both cost efficient because you're not paying for a piece of hardware that's not working at full potential, but it's also performance efficient in the sense that all of the underlying storage devices are operating at their full potential. You don't have an extra 10 hard drives there that are whose performance can't make it out to the network, right? If you put this together in an overall storage cluster, then you're getting the full performance out of all of the storage devices that are part of the cluster. Hello. There we go. So this is a benchmark, 12 nodes through 32 nodes of the new product. The solid lines are the aggregate performance as we increase the number of storage nodes in the cluster. It's very nicely linear, both in terms of lack of bumpiness, but also in terms of it's got the right slope to it. The horizontal dashed lines are the output per node, and we like the fact that those are horizontal. It means that as you increase the scale of this, the amount that each node is contributing to the overall performance is not going down. So that's again a measure of linearity. So this graph only goes to 32 just because this is the test that we ran. We're currently in beta, and so this is the test we've got so far. We have a current customer with a prior generation of hardware that has, I think, 1,500 storage nodes. And as they grew from small to all the way up to 1,500, they were seeing linear performance increases all along the way. And the software that governs the new OSD is the same as the one governing the old one. And so we have no reason to believe that the new OSD won't be just as linear all the way out to 1,000 nodes. As I said, great architecture leads to great performance. So ActiveStor Ultra hardware. Okay, so I wanted to go through just a little bit of this to show you can get some idea of the specifics of what we're talking about here. On the, let's see, your left, that is the metadata processing engine. That's a commodity standard server, 4 nodes. In this case, it's got 96 gig memory, 8 gigabit NVDIMM, and dual 40 gigabit Ethernet ports. On the right, yes, you're right, is the new storage node. There are 4 nodes in that. We have 6 hard drives facing out the front. In our case, that's the customer selectable capacity, right? 4 terabyte drives or 10, 12, or even 14 terabyte hard drives. In the back, there is space for 1 or 2 SSDs. Again, that's selectable. You could decide that you have a lot of small files in your workload, and so you can provision more small file storage. It comes by default with dual 25 gig E. You can put InfiniBand in there instead. One thing that's interesting to note, in this case I saved this for this slide, is that these nodes actually have 32 gigabytes of RAM in each one. So if you're talking 32 nodes in your cluster, which is a fairly small number, that's a terabyte of DRAM to cache your working set of data. So that as you grow your storage cluster, you're actually growing network bandwidth and DRAM caching and processing power and storage devices all at the same time. So ActiveStor Ultra with PanFS 8. PanFS 8 is the latest version that enables this new hardware. For us, this is starting a new era of innovation and performance. We have this completes our transition to COTS, right? We had been using a proprietary custom hardware solution for years before, and now we've finished the transition to COTS. We're pretty excited about it. We're getting higher performance because of the new software algorithms inside the system. We're getting more consistent performance because we are using the devices for what each is good at. The hard drives for large files and small files on SATA, etc., on SSD. Over time, we will have a wider choice of platforms. We're shipping with this one that I showed you a second ago as our first release. After that, we will be branching out into more different kinds of OSD hardware. Latest networking and storage media, because it's now COTS, it'll be easy for us to, with Linux, move to the latest speeds and feeds of all those. Higher density. It's actually kind of difficult to find the right balance of processing power and network speed and storage capacity in the same box. It's easy to find a tub of drives with 90 drives and a smaller CPU, but you can't light up all 90 drives if you have that. You can't move that. You don't have enough NIC bandwidth, enough CPU power in between to drive all of those. So, but we're happy that we found a good compromise for this first release. Instantaneous snapshots. The system has been designed ground up to do much better at snapshots. They haven't traditionally been a big deal in the HPC business, but we think that data management feature is going to be start of a trend. We'll need a lot more data management features, and so snapshots are a good thing. And for us, higher feature velocity because we're leveraging COTS and open source. Come on. There we go. Come see us in booth C1111. You'll see the live hardware and a demo of the running system. Thank you.